Good day, stat students. So today we're going to talk about section 9.2 part 2. If you check out parts 2, 3, and 4, all they are is running hypothesis testing for the population portion P. They're just different problems, and I separated them into different parts. Okay. So here's the first example. We test if the percentage of all Ohio drivers that wear their seatbelt while driving is less than 90% and an alpha of 0.1. We randomly select 200 Ohio drivers, and 166 indicated they always wear their seatbelts while driving. So the first thing is, how do we know that we're conducting a hypothesis test? Well, we know that we're conducting a hypothesis test because it says we test. Okay, right there. That gives you the idea that we're running a hypothesis test. But the other thing is that we have stated an alpha significance level. Okay, we didn't state a confidence level like 90% or 95% like in a confidence interval. Okay, so those are two indications that you're probably running a hypothesis test. What's the variable? Well, do they always wear their seatbelts while driving? It's a yes or no type question. It's categorical. Once the data is categorical, what are we going to have to do? We're going to have to analyze the data with a percentage or proportion. That's why we're testing the population portion P. All right, hopefully that makes sense. What was our sample? It was 200 Ohio drivers, right? We randomly select 200 Ohio drivers. And if that means n is equal to 200, that means if we looked at 200 Ohio drivers, that must have meant our population was what? All Ohio drivers. What would be a success here? Success would be finding a person that always wears their seatbelt while driving. And so how many people indicated that they always wore their seatbelts while driving? It looks like, let's see, it looks like 166 indicated they always wear their seatbelts while driving. That's X in the problem. So now we have X, we have N, and we're going to have to calculate what? P hat, right? The sample proportion. So that would be 166 divided by 200, or 0.83. Hopefully you got your calculator out. Okay. You can think of it as 83%. So 83% of the sample of drivers are wearing their seatbelts all the time while driving. All right. I like to think of it as 0.83 because that's the way we're going to have to put it into our test statistic as a decimal. All right, so there's the background information. Now we can get into the different steps of hypothesis testing. Step number 1, state the hypotheses. So we always like to state our alternative first, okay? And let's see, and that's going to be stated probably right in the problem. So what are we testing? We're testing if the percentage is what? Of some sort of population is less than 90%. Sounds like the alternative to me. So you can put it as P is less than 0.9 or P is less than 90%. So P here is standing for a lot of words. Okay, instead of writing all those words out, we just go ahead and get to place the symbol there. So we could state this. We could state what we're testing is the percentage of Ohio drivers that wear their seatbelts all the time while driving. Okay, that would be P in the problem. And so we could write all that out, but we're just going to state the symbol. Okay. So we go back to the null. The null is going to have the equal to sign. So P is equal to 0.9. All right, or P is equal to 90%. That means P sub 0, remember P sub 0 is the value in the null hypothesis. Okay, so that's P sub 0 there, 0.9. Okay, step 1, you got it. Step 2, check the conditions. All right, so we either need a random sample or was the data obtained with an experiment? Well, it looks like we randomly selected people, so we had a random sample. Check mark. And 2, we got to go ahead and verify the central limit theorem, the CLT, because we got to make sure that the sampling distribution of P hat is approximately normal. Okay. So what we're going to have to do, remember back in chapter 7 we said that if n times P was greater than or equal to 15 and n times 1 minus P was greater than or equal to 15, okay, we would verify the central limit theorem. Remember that back in chapter 7? Okay, so for hypothesis testing purposes, if we're testing the population portion P, we have an assumed value for the null hypothesis. It's what? P sub 0, and we use it here. Okay, since there's an assumption, we have a value for that we're temporarily going to assume for P, we use it here. So what we're going to do for a hypothesis test, we're going to verify if n times P sub 0 is greater than or equal to 15 and n times 1 minus P sub 0 is greater than or equal to 15. Now, before we do that for this problem, I want to make sure you understand this and separate the two. We don't have an assumed value for P in a confidence interval. So remember, for a confidence interval, we had to figure out if n times p hat, which is equal to x, was greater than or equal to 15. So notice there are differences in the conditions with regards to if we're testing a hypothesis, if we're doing a hypothesis test or if we're doing a confidence interval for p. Okay, so make sure that you read those two lines there and keep them straight. Okay, let's go ahead and verify this for our hypothesis test here. So we got to make sure that n times p sub 0, which does not equal x, okay, so we need to do the calculation here. So n times p sub 0 is equal to 200 times 0.9, that's the value in the null hypothesis. That's 180. That's certainly greater than or equal to 15, check mark. So we got one half of it. We got to do the other half of it, okay. That's 200 times 1 minus 0.9. That would be equal to 20. That's certainly greater than or equal to 15, check mark. Okay. What does that mean? Since they're both greater than or equal to 15, the CLT applies, and the sampling distribution of p hat is approximately normal. Yay! That means we can use the formula that I've been giving you for the test statistic and move on using the standard normal table here. Step 3, calculate the test stat. So here's our test stat. Okay. This should look familiar. I think we have everything that we need. So there's the null, an alternative hypothesis, so we know p sub 0 is equal to 0.9, so we know what to throw in there for that. We know that n was 200, and I think our p hat, remember that was the 166 over 200, that was the 0.83. So I think we have everything that we need. So here's the big old formula, okay? So 0.83 minus 0.9, 0.9, 1 minus 0.9 divided by 200. Remember, no rounding in here. Don't do any much rounding in here. We're going to round here in the end, and it turns out to be a negative 3.30. So again, if you're going to put this in your calculator all at once, make sure you put parentheses around here, put parentheses around here, okay? And check out the last video on how to calculate the test statistic if you forgot how to do that in your calculator, okay? Or you're going to have to do these in separate pieces parts, no rounding. I put it to 5 decimal places here, or excuse me, 4 decimal places here, but I prefer that you just left all the values in your calculator and came out with the right value for your test statistic. Okay, so only round it here, and we're going to round to 2 decimal places. Okay, so our test stat turned out to be a negative 3.30. What does that mean? So here's the interpretation of the test statistic. That means our sample proportion, our p hat from our random sample, okay, is what? 3.30 standard errors, what? Below, because it's negative, the value in the null hypothesis. Remember, that's what we're trying to figure out. How many standard errors is our p hat from the value in the null? It's 3.30 standard errors below the value in the null hypothesis. So there's our test stat. Remember, we have a left-tail test, okay, and so that plays into step number 4, calculating the probability value, the p-value, okay. So we have a left-tail test, all right, and so we have a negative 3.30. All right, and so let's see here. So here's our table. That, remember, so if you don't have your standard normal table out, please get it. Okay, I'm going to go back to the last slide here and try to demonstrate this. I didn't do this on StatCrunch. It's kind of a pain to do it on StatCrunch. It's actually kind of just easier to just draw it. It's just a little more sloppy. So here's 0. Here's a negative 1. Here's a negative 2. Negative 3, we should just about be to the end of the graph, but we know that there's a little bit more area back there. So my goodness, a negative 3.30 is way out here. Okay, we have a left-tail test, so it's this tiny little area out here. So does that, the part that we shaded in, did it look like I shaded in a whole lot underneath that graph? No. So our p-value should be really, 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 really small. Okay, so let's look up a negative 3.30. Negative 3.3, 0.00. We see where that comes together. I got here 0.0005. There's our p-value. Okay, remember for a left-tail test, you could just look it up on the standard normal table. You got it. Nothing else to do. Okay, so there's our p-value. So we get to go to our conclusion now. All right. So a reminder, if the p-value is less than or equal to the significance level, we're going to reject the null hypothesis. That's important to remember. Okay. If p-value is greater than the significance level, do not reject the null hypothesis. So what are we going to do here? Oh, by the way, I'm going to state it right now. So if you do not reject the null hypothesis, don't ever accept the null hypothesis as being true. Okay, we're going to talk about that more because it doesn't in another problem because it doesn't apply here. I just wanted to state it very clearly right now. So don't ever accept the null hypothesis as being true. Okay, we're going to say do not reject. That's difference. That is a difference versus accepting the null. So do not reject the null is going to be the wording. Not accepting the null. We'll talk about that later on when we get to a problem like that. Here, since the p-value is equal to 0.0005, which is smaller, much smaller than the significance level of 0.1, okay, what are we going to do? We're going to reject the null hypothesis. And when we reject the null, what does that mean we think about the alternative? We think it's correct. Okay, so when you reject the null, we think that the alternative is correct. And we just got to state this in words. So remember what was in the alternative. We said P, which stands for some wording here, is the percentage of all Ohio drivers that wear their seatbelts all the time while driving. Okay, that's what we think based upon our results. Okay, because why? Because our p hat was 0.83, which is a lot smaller. I mean, it's really far away from this. So we think there's no real chance. It's a small chance, right? Remember that p-value? It's a small chance that that this is not going to be less than 0.9. So we think that's true, and we just got to state that in terms of the problem. So, conclusion, the interpretation. So, when you reject the null hypothesis, what we're going to say in our conclusion is that we have strong evidence. Now, you might also see this being said as we have sufficient evidence. We have statistically significant evidence. Okay? All that stuff is saying the same exact thing. I'm just going to start off. We have strong evidence at the 10% significance level that less than, what, 90% of all Ohio drivers constantly wear their seatbelts while driving. So in other words, P is what? Less than 90%. That's it. Okay? So we have strong evidence of this at an alpha of 10%. There you go. That's all you have to do for the conclusion. It's fairly straightforward when you reject the null hypothesis. We have strong evidence. We have sufficiently statistically significant evidence. We have sufficient evidence, okay, of what? That the alternative is correct. And all you got to do is state that in words, okay? And as long as you can state that in words, you should be good, okay? Now, we're going to have to do something a little different when we say do not reject the null hypothesis, but that's for another problem, okay? So there's our 5 steps, okay? And in part 3, okay, we'll do the second problem. All right. Thank you for your time.